Alright, science fans, let's dive deep into one of the most powerful and controversial creations of human ingenuity, the nuclear bomb. You've probably heard words like fission, fusion, and atomic bomb thrown around, but how do these things actually work? And what makes them so devastating? Let's break it down. At the heart of every nuclear bomb is a simple but mind-blowing concept harnessing the energy locked inside atoms. There are two main ways to do this: splitting heavy atoms apart or smashing light ones together. That's fission and fusion. First up, the fission bomb, also known as the atomic bomb or A-bomb. This is the kind of bomb dropped on Hiroshima and Nagasaki in 1945. The science here is all about splitting heavy elements like uranium-235 or plutonium-239. Imagine a massive nucleus just sitting there. Hit it with a neutron and it splits into two smaller nuclei, releasing a huge amount of energy, and crucially, more neutrons. These new neutrons go on to split more nuclei, setting off a chain reaction that multiplies in microseconds. But how do you build one? You need fissile material, highly enriched uranium or plutonium. Wrap it with specially shaped explosive lenses that compress the core evenly. That's the implosion method. There's also a neutron initiator, which injects the right number of neutrons at the perfect moment, and a tamper or reflector to bounce stray neutrons back into the core. When the explosives fire, they squeeze the fissile material into a supercritical mass, kicking off the chain reaction. In a blink, energy is unleashed as a massive fireball, shockwaves, searing heat, and deadly radiation. Now let's turn up the heat. The fusion bomb, aka the hydrogen bomb or H-bomb. This takes the energy game to a whole new level. Fusion is when light nuclei, like deuterium and tritium, smash together to form helium, releasing even more energy than fission. But fusion needs insane temperatures and pressures, so how do you get those? By using a fission bomb as a trigger. Here's how it works. The primary stage is a regular fission bomb. When it explodes, it blasts out a flood of X-rays. These X-rays race down a radiation channel to the secondary stage, which contains fusion fuel, usually lithium deuteride, and sometimes extra uranium. The heat and pressure from the X-rays compress this fuel until fusion kicks in. Even cooler, fusion releases a burst of fast neutrons which can trigger even more fission in a uranium tamper. The result? A bomb thousands of times more powerful than a simple A-bomb. Now what actually happens when one of these detonates? First there's the blast wave, flattening everything for miles. The thermal radiation burns and ignites fires across entire cities. Initial radiation delivers lethal doses of gamma rays and neutrons in just seconds. Fallout, radioactive debris, spreads for miles, poisoning land and water. And don't forget the EMP, which fries electronics over huge distances. Some infamous examples: Little Boy and Fat Man were fission bombs dropped in 1945 with yields of 15 and 21 kilotons. The USSR's Tsar Bomba, a fusion monster, hit around 50 megatons, by far the largest ever. And Ivy Mike was the first full-scale H-bomb test, clocking in at over 10 megatons. But with such power comes serious risks and responsibilities. Long-term radiation can cause cancer, genetic damage, and environmental devastation. There's always the threat of proliferation, these weapons falling into the wrong hands. That's why global treaties like the Nuclear Non-Proliferation Treaty exist, to limit spread and encourage disarmament. So, next time you hear about nuclear weapons, remember, it's all about the science of splitting and fusing atoms, but the consequences reach far beyond the lab.